So it's Friday. That's always good, and it's our last Friday together. Uh, again, next week we have uh, class Monday through Thursday, and then that's it. That's our last day of class, and then our last test is the following Tuesday morning at 8. So almost over. What we're going to do today is continue the topic we were discussing yesterday. And this is combined axial loads and bending moments acting on members together. And what we looked at yesterday was we had an axial load and we were just bending about the z-axis. What we're going to do today is talk about bending about both the z and the y-axis. So that's what we're going to start with today, is bending about both the z and the y axes. So we're just basically going to add one more thing to what we were doing yesterday. I'll remind you about the sign convention. And again, this would be if you're going to substitute into those formulas, then this would be the sign convention you would use to determine whether you're substituting in positive y, positive z, a positive moment or a negative moment. And our coordinate system, remember, the origin of our coordinate system is at the centroid of the cross section. And we're looking at that cross section. Y is vertical, z is horizontal. And we, again, define a positive axial load P as being in the positive axial direction. Also note it causes tension. Right, we did this yesterday, and again, all of this is based on, as far as the moments go, it's based on right hand rule. So you take your right hand, stick your thumb in the positive direction your fingers go. That's considered a positive moment. So if a moment about the z-axis is in this direction, that would be considered a positive moment. Well, the same thing if you look at the y. If you stick your right thumb in the positive y direction, the direction your fingers curl, that's defined to be a positive moment about the y-axis. And so that's the sign convention we will use if we're going to plug in that formula. Remember, I also discussed yesterday, if you don't want a formula, use the sign convention and you can just look and tell if it's causing tension or compression. And just, assign plus or minus based on tension and compression and just put in magnitudes. That works too. All right, well, let's look at an example of how we might wind up bending something about both the axes. We'll try to draw a three-dimensional picture here. Let's assume we got this member. My coordinate system on here. Right, so again, our x direction is the axial direction. This is z, this is y. The example we looked at yesterday, right, we applied an axial force, not through the centroid, but it was out on one of the edges. Right? But it was still on if I remember right, I think it was on the y-axis maybe. But it was out here at the edge. And so that resulted in an axial load and a moment about the z-axis. What if we come up out here somewhere. Pretend like that's straight up. Apply some axial force P. It's not on either edge, so this would be some distance, we'll call it dy, away from the z-axis. And some distance, we'll call it dz, away from the y-axis. All right, well, if you do that, that's going to result in not only an axial load, but a bending moment about both the z-axis and the y-axis. So if we come down here somewhere, cut this, it's A, B, D, and D. The E would be that back corner that's hidden. And let's look at that cross section. My coordinate system. All right, so we talked about equivalent loading systems. So what we did was we replaced that force with an equivalent force and moment, putting the force at the centroid. So we can do the same thing. We can replace this loading with our axial force acting there at the centroid. And looking at the location of this force P, right? This force P, if it's acting up where it's shown on this picture, right, that's going to cause a moment this direction about the z-axis. Right? So we're going to have this moment, call it mz, right? It's going to act in that direction. And if you go to our sign convention, right, this direction would be a positive moment. So this is actually going to be a positive moment if you're going to use the sign convention. And the magnitude of that moment would be that force, P, times the distance it is from the z-axis, this distance dy. So it would be force P times this distance dy. Whereas if we look at this force applied at that point shown there, it's going to cause a moment this direction, right, about the y-axis. Right? If we're pulling up to the left of the y-axis, it's going to want to rotate that direction. So we're going to have a moment in this direction. We'll call it my. And going back to our sign convention, right-hand rule says that is in the positive direction. So this would be a positive moment. And it would be equal to that force times this distance it is away from the y-axis, which I call dz. So we wind up with an axial load and moments about both the y and the z-axis. So when we calculate our normal stress, right, we've got same formula that we had yesterday, P over A minus my over I. But here I'm going to specifically differentiate between, since now we got moments about the z and the y, what we did yesterday, the moment about the z times the distance y away from the z-axis. That's divided by Iz. Now we have going to get another normal stress due to this moment about the y-axis. So that would be moment about the y times z, the distance away from the y-axis, divided by the moment of inertia about the y-axis. That's the axis we're bending this thing about. So all we've done is add this term to what we did yesterday. And again, this formula with the, again, the minus and the plus here, that corresponds to if you're using, again, this sign convention. So if you're going to plug in this formula and use this minus sign, this plus sign, then all these values for m and z and y, you got to plug in the right sign based on this sign convention. Now, again, just reiterate here. If you don't like doing it that way, right, you can just do, say, think of it as plus or minus p over a, plus or minus mzy over iz, and plus or minus myz over iy. And here, those plus or minus signs are based on you just looking at it and telling, right, is this force P causing tension or compression? Tension plus, compression minus. This moment about the z-axis, is it causing tension or compression at this point that you're calculating the stress? It's causing tension, you put a plus there. It's causing compression, you put a minus. Same thing for the last term. And you just put in magnitudes for the moments and these distance y's and z's. You don't take into account whether it's in the positive or negative direction. So that also works. And I think I mentioned this yesterday. I think it's worth your while to understand this approach. Even if you want to use the sign convention and plug in this formula, that is fine. That is a great way to make sure you get all your signs correct. But even if you do that, if you kind of understand this concept, it's a way to check yourself, right? So, for example, let's come back to this cross section. We'll label these points A and B, and I reckon I put that right on top of D. And we'll call this E right here. So let's see if we can just, we're not obviously calculating or putting in any numbers, but we should be able to just look and tell if this load is going to cause tension or compression at each of those points. So let's, I'm going to make a little table over here. You can still see. So say we're calculating the stress at each of those 4 points, the 4 corners. And I'm going to make a column here for the stress due to each one of those loads. So I'll call this the stress due to the axial force P, the stress due to the moment mz, and then the stress due to the moment my. And again, we're not putting in any, I'm not going to write the formula. All we're doing is looking and seeing, is this causing tension or compression? Right? So first up, axial force P. Obviously, it's acting up, it's pulling on this thing, it's in tension. So that axial load P is causing tension everywhere. Right? It's causing tension on that entire cross section. So it doesn't matter which point you're at. All of those P over A terms are going to be positive for any point on that cross section. Right? But now let's look at this moment mz. Right? It's acting in this direction that I've got shown here. So if we got a moment that's acting in this direction, then this moment here, it's causing compression everywhere above the z-axis. Anywhere up above the z-axis is going to be compression. Anywhere below, it's causing tension. So this moment mz, anywhere above the z-axis is going to be compression. So if I'm getting a stress at A, it's in compression. That term is going to be negative. The stress at E, it's in compression. It's going to be negative. Now, conversely, that moment mz, anywhere below the z-axis is causing tension. So any point below the z-axis, the stress due to that moment is going to be positive for tension. So I know the stress at B and D for that moment is going to cause tension, be a positive term. And then finally, this moment my, right, if it's acting this way, in this direction, right, it's causing compression everywhere. You want to think of above the y-axis, and everywhere below the y-axis, it's causing tension. So for the stress due to my, right, the stress due for this one, it looks like E and D would both be negative because they're in compression, and everything on this side of the y-axis, like A and B, would be tension. It's negative, it's both be positive. So it's relatively, should be anyway, straightforward concept that you can look at the direction of these moments and determine if it's going to cause tension or compression at that point. And that would determine, again, what sign you put there. And you just put in magnitudes if you're actually going to calculate it this way. If you're going to use the sign convention, and if you have time, it's worth your while maybe to go back and check yourself and see, okay, well, I know this moment's causing tension here. I better have a positive term here. And if you're looking at, say, point D, I know it's causing compression at D. This term better come out negative if I'm calculating the stress at D. All right. So enough general stuff. Let's see if we can put some numbers in here and actually solve a problem. Any questions at this point before we do go to a particular example? All right, great. Let's do this one. Let's let me draw my picture here. This may not be real pretty. All right, so we've got this, remember, this corner, this is A, this is B, this is D and E. And we're applying an axial, let's see if I can try to draw this straight. Ooh, it's going to go right out through. Yeah, that's kind of. Axial force P is 1,000 pounds. Right, and it's acting straight down the member, but it's applied right at that corner A. When you look at the cross section, this is 8 inches, and this is 6 inches. So the cross section is a rectangle, 8 inches tall, 6 inches wide. And we're going to apply this axial force of 1,000 pounds at one of the corners. And we want to find the normal stress at, I don't know, we'll do a couple of points. How about A, B, and I don't know, maybe we'll do 3. We'll do 3 of the 4 corners. All right, so again, what we're going to do now is kind of replace that one force acting at the corner with the force at the centroid and adding the moments that this force causes. And in addition to that, we'll be, we've got to put our coordinate system on there as well. So we know the origin of my coordinate system, again, is going to be right at the centroid. And we'll call this Y and Z. So what we're going to do is take that 1,000 pound force, right, and we're going to move that to the centroid. So I got P is 1,000 pounds. So remember that force was acting at the corner A. So if that force was applied up here in this direction, that's going to cause a moment about the z-axis in this direction. And what's the magnitude of that moment? Anybody paying attention here and can tell me? If I apply this force of 1,000 pounds at the corner A, it's going to cause a moment about the z-axis in this direction. And what would the magnitude of that moment be? Easy math you can do in your head. You don't need to calculate.
$6,000.
Where'd you get 6?
The P times the 6 inches.
Remember that moment would be the force times the distance it is away from the z-axis.
4,000.
So it would be 4,000, right? If this is 8 inches tall, this is 4 inches. This is 4 inches, right? The centroid's right in the middle of a rectangle. So this would be a 4,000 these inch pounds in that direction. And so now you should be able to tell me what the moment about the y-axis, what its magnitude. It's going to be in this direction, right? Agreed? You apply this force over here at the left side. It's to the left of the y-axis. It wants to rotate that direction. And what would that moment be? I got an answer already. They think 3,000, correct. So this would be 3,000 inch pounds in that direction. Again, I'll put my points on here. So here's A, D, E, and B. This, again, if that's 6 inches, this is 3 inches. This is 3 inches. So that's where the 3,000 came from. It's the distance away from the y-axis is 3 inches. So this is, again, 1,000 times 4 inches is 1,000 times 3 inches. All right, any question at this point how we got from this to this force and the two moments? All right, so at this point, if you're just going to base it on tension or compression, you could go ahead and, start plugging in numbers. If you're going to use the sign convention, then we need to determine, again, are these values positive or negative? So sign convention says this is a positive direction for a moment, and then about the y-axis, this would be a positive direction. Our axial force P is in the negative direction. It's causing compression. So again, if we're doing sign convention here, P would be a negative 1,000 pounds. MZ, if it's in this direction, it's positive. It would be a positive 4,000 inch pounds. My, right, if this is the positive direction, our moment's in the opposite direction. That is a negative moment. So minus 3,000 inch pounds. All right, any question about as far as the signs go there? Now, we're going to plug in this formula. If we're going to use the sign convention, then we've got sigma is equal to P over A minus my over I. This is mz times y over iz. And then plus my times z over iy. So we need to know what the area is. We need to know what the moment of inertia about the z-axis is, and we need to know the moment of inertia about the y-axis. So let's calculate those. Area is easy. It's 6 by 8, 48 inches squared. IZ, remember I for rectangle, the z-axis goes through the centroid, so it's 1/12 base times height cubed. So this would be 1/12. With respect to the z-axis, the base is 6, and the height is 8. I calculated that somewhere. Let's see. I've got 256 inches to the 4th. IY, right, with respect to the y-axis, 8 inches is the base, and 6 is the height. We just interchange the base and height. So it'll be 1/12, 8 times 6 cubed. And that's 144. Right? So now, as far as when we calculate the stress at different points, we discussed this yesterday also. The only thing that changes is, well, yesterday it was just the y. Today, it would be y and z. That's the only thing that changes when we move to a different point, right? None of these moments change. None of the force doesn't change. The moments of inertia, none of that changes. The only thing that's going to change is the location, and that's y and z. So if we want to find the stress at A, for example, again, sticking with our sign convention, here's point A. So y is going to be positive 4. It'll be a positive 4. And the z location for point A, positive z is this way, so it would be a positive 3. Yeah, we just plug in the formula to get the stress at A. We got P's minus 1,000. Our area is 48 minus MZ was a positive 4,000. Y is positive 4. IZ is 256. And plus MY is a negative 3,000. Z for point A is a positive 3. And IY was 144. And we add those up. And that will tell me the stress at A. If it comes out positive, that means that combined loading is causing tension at A. If it comes out negative, it means that combined loading is causing compression at A. And this, if I push the right numbers in my calculator, I got a negative 145, let's say 0.8. This would be PSI. So point A is in compression due to that combined loading there. All right, any question about what we did to get the normal stress at point A? All right, so if we go to a different point, the only thing that's going to change are my Y's and Z's. So if we go to point B here, now I'm looking at B. Y is still going to be positive, right? It's in the positive Y direction. So YB would be a positive 4. Z, though, is going to be negative, right? Because positive Z is to the left here. Point B is to the right. So it would be a negative 3. And we plug those values for Y and Z into the formula, and we get the stress at B. So the stress at B minus 1,000 over 48, that doesn't change, minus 4,000. Y is still positive 4. 256 minus 3,000. But here, ZB is -3, so that changes. This is a -3 over 144. And we add those up. And I got also negative. Not as large, so I got 20.8 PSI. All right, any question about how we got the stress at B? All right, well, I changed my mind. Instead of doing the other corner, let's just let's just pick a point. Let's see, man, I got more room. I can we'll put it here. So this is point, we'll call this point G. And let's say this is, I don't know, so 2.5 inches below the z-axis. Let's say that would be, I don't know, say 2 inches. So if we wanted to compute what the normal stress was at that point G, yeah, the only thing that's going to change is the location, Y and Z. So Y at this point, now it's in the negative Y direction, would be a negative 2.5. And Z coordinate for that point, it's in the positive Z direction, so it'd be a positive 2. So to get the normal stress at G, still minus 1,000 over 48, minus 4,000. Here's where we put in our Y coordinate. It's a negative 2.5. 256, negative 3,000. And then we got a new Z coordinate here. It's positive 2. And add those up. And since I just made this up, somebody's industrious and wants to take your calculator and add that up, that would be okay, but not necessary. Any questions about this? This is not hard. And again, the last thing I'll mention is, if you don't want to use the sign convention and you want to use hey, I can just look and tell. That 4,000 inch-pound moment about the Z, it's causing compression at A. I know this term is going to be negative. And you see, it's negative. I know that 4,000 inch-pound moment is causing tension at G. So this term should be positive. Negative times negative is positive. All right, so we got an answer. Zach for this. He says it's minus 44.3. So this is for Zach. So I don't know if somebody else confirms that or not, but again, you just add those up and that's what you would get. All right. So any other question about combined axial and bending? Okay. Yeah, don't overcomplicate this. Like I said, I think I mentioned this yesterday. I've seen students do weird things on problems like this, where they'll go calculate, get a different moment for a different point. This moment in the formula, that's the moment acting on the cross section. It doesn't change where you're at. So don't do weird stuff. You got this formula here, and it should be pretty straightforward to calculate the stress at any point on the cross section that you want. But it's anything, it takes practice. The more you practice, the better you get at it. So hopefully the intent of, you sat here and watched me go through this. There's examples in the book. You can look at those. But you got to sit down and work through some of those suggested problems out of the book on your own. If you do that, I think you'll find it's not that complex a problem.
Could you explain how you got the moment about Z and Y again?
All right. What I did was to get the. Okay, so here's Z. This is 4 inches. This is 4 inches. So the moment that this force causes about the Z-axis is this force times that distance. That's the distance away from the Z-axis. So it would be 1,000 pounds times 4 inches. And again, if this is defined as a positive, that's a positive moment. It's just the force times the distance from the axis.
Gotcha. Okay.
Same thing to get the moment about the y-axis. We took this force times the distance away from the y-axis, which, again, based on our sign convention, is negative, right? And that distance was 3. Right? Any other questions, again, related to this particular problem or just in general, combine axial and bending? And I told you yesterday, we're not doing axial bending and twisting. We're just doing axial and bending. If you aerospace majors, when you take structural analysis 1, you're going to do axial loads, bending, twisting, temperature change, multiple materials. You're going to do everything. This formula right here is going to turn into some ungodly, nasty looking thing. So something to look forward to for your aerospace major. But not in this class. Right? That's all we need in this class. All right, so that's all we're doing in chapter 8. And now we're going to skip ahead to chapter 12 and talk about the deflection of beams. And that's basically all chapter 12 is about. And we're not going to do all of chapter 12 for a couple of reasons. One, we don't have time to do everything in chapter 12, and even in the regular semester, we don't do everything in chapter 12, because what you'll find in chapter 12, it's a bunch of different methods. And you go to, this section will do it one way, and then you go to the next section, it's the same thing. It's all determining how much a beam deflects, how much it bends. It's just using different methods. And there's no need to go through. There's about I know at least 4, maybe 5 different methods to do this. And we're going to look at 2, right? So just FYI for information purposes. Again, there's several methods to find the deflection or displacement of a beam. And one, you don't need to know how, there's nothing really, to me, I don't know, value to be gained to know how to do something 6 different ways. And again, time wouldn't allow us to do all the different ways anyway, right? We're going to look at 2. So that's what we're going to do. And in chapter 12. The first method we're going to look at, come on, focus there. It's called the double integration method. The second one's going to be, we're going to make use of superposition. Right? So those are the two things that we're going to do in chapter 12. And it's just two different methods to determine the deflection or displacement of a beam, right? We've been talking about beams and we'll say they bend. Well, now we want to look at how much does it bend. That's what chapter 12 is about. So today, we're just going to take about, somewhere between 5 to 10 minutes to kind of introduce you to this first method. This is the first one covered. It's in the first couple of sections. And we're going to determine slope and displacement by using this double integration method. As you might guess from the title, somewhere in here it's going to require us to integrate twice. And you'll see where in a minute. But all I want to get to today is this relationship. If you go back when in chapter 6, when we were deriving that formula for bending stress, minus my over I, we went through some of this, and so I'm not going to go through everything that I went through back then in chapter 6, but you could go back and look in your book or look in your notes, or go back and find the video when we did this in class. We took this beam and we applied this bending moment, and we defined the radius of curvature, rho. So remember, rho here was the radius of curvature. When we first got our formula for stress in terms of rho, it had that radius in it, but then we wanted to get rid of that rho and get our moment in there, and that's what we did. But you go back and look, again, I'm not going through all this, we came up with this relationship, that the bending moment was equal to EI over rho. And again, I'm not going back, starting from scratch and showing you where we got that. So just take my word, that was one of the things we found. But we're going to take that now and, right, if we divide both sides by EI, we get that the moment 1 over rho is equal to the moment divided by EI. And also note here that M is a function of X. And so that M is some function of X. This X-axis being our longitudinal axis. And that's what we did when the first way we looked at drawing shear moment diagram. We actually found the equation for that moment. We cut it and we got an equation for V and M. But then we looked at a shorter, easier way to draw the shear moment diagram. But I told you at the time, you needed to know how to do that, not necessarily to draw the shear moment diagrams, but we were going to use it later. And this is where we were going to use it. All right, you're going to see the deflection and what the form shape that beam takes depends on what that moment function is. So we're going to have to go back and do what we did at the beginning of chapter 6. Use method of sections, cut the beam at some arbitrary location X, and get that moment equation. All right, but that will come tomorrow. So the last thing I wanted to do here was Again, this you can look in your calculus book. If you look up curvature in the index in your calculus book, and you'll see something similar to this. If you've got just some arbitrary curved path, it doesn't matter. It's just y some function of x. If you look at some point on that curve, right, this y, that's going to be our displacement. But at that point on the curve, there's going to be some radius of curvature. Obviously, if it's a circle, then it's the radius of the circle. But it's just some arbitrary curve. At that point, it has a radius of curvature. And this radius of curvature is given by this formula. And this is why, again, I'm not going through and deriving this, but it's 1 plus the first derivative squared, all raised to the 3/2 power. And all that is divided by the absolute value of the second derivative. And I'm pretty sure a few of you that are in this class, I don't know if you're in attendance today or not, but if you were in my dynamics class, that should look familiar. We use that in dynamics as well. But again, I'm not going through and deriving this. You just can, if you're really curious where it comes from, go to your calculus book. But that's the radius of curvature for that curve at that particular point. Well, for our purposes, we didn't get to do this in dynamics, but dy dx, this term in the numerator, that's the slope. And that would be, if you look at the tangent line here, again, that's the tangent line. The slope would be tangent theta. Right? The slope of, that's what the derivative is, the slope of the tangent line. And the slope rise over run. But for our purposes, that's approximately equal to theta. Or very small angle theta. Remember when we did axial deformation, we said we're always going to be seeing really small deformations, and we use that to simplify things. Well, we're going to use the same concept here. If you've got an actual beam and you bend it, probably it's going to be almost hard to see, unless you got a really long beam. We're talking about really, really small deflections. We're not talking about like a diving board when somebody jumps on it and it bends way down. That's not what you typically see in real structures. So if dy dx is equal to essentially the angle theta, and that angle theta is really, really small, then again, dy dx squared, remember we're squaring it, you take something really small and square it, is very, very small. Essentially, we're going to neglect that. So if that dy dx squared in the numerator is essentially 0, well, 1 to the 3/2 power is just 1. So what we get then is that numerator if that is, again, essentially 0, that's equal to 1. So if we take this and invert it, 1 over rho is just equal to the second derivative. And also notice I dropped the absolute value. we can do that if we base our our sign convention. A positive moment causes it to bend this way, right? That's a positive moment, and that causes it to be concave up. Well, that's what the second derivative tells you, right? It's concavity. If it's positive, it's concave up. So if I got a positive moment causing concave up, I can get rid of the absolute value there. So if 1 over rho is equal to the second derivative of my deflection curve, it's also equal to m over EI. So if we take, we'll call this 1 and call this 2, and put those two things together, then what I've got is the second derivative of my displacement function y is equal to m over EI. And this is and that's what we're going to use on Monday, is we're going to use this relationship to calculate what the actual displacement function y is. And we'll talk about this Monday, but this is actually a differential equation. So some of you who had DE should know how to solve this, but rest assured, if you haven't had DE, I can show you how to solve this differential equation. It's one of the easiest differential equations there is to solve. You'll be able to solve it with what I show you without having taken differential equations. That's what we're going to do to start with on Monday. And then, again, Monday, Tuesday, Wednesday, we'll talk about beam deflections, and that'll be it. All right. Any questions at this point about how or where this came from? All right. Well, then that's it for today. That's it for the week. I will, as always, stick around, though, if somebody does want to hang on after I start recording, then I'll be glad to answer any questions you have. Otherwise, have a good weekend, and we'll pick up here Monday.